Okay, first thing, this function that we came up with, we called the net accumulation function. Right here. Where did that come from? What was the origin of that net accumulation function? We said it was the most important thing of last Monday's lecture. There we go. Okay, so yeah, so that thing came from this is what is this? So this is a change in y function or a change in height function, right? It always gives us values of change in height, and we can find those changes in height by the rate of change times the change in our independent variable, in this case, time since we started lowering. But this change in y was for what? Time since 0.6 seconds, right? All right, so this gave us a change in height since that 0.6 second mark. So at the 0.6 second mark, how much change in height do we have? 0, right? That's why that graph shows that at 0.6 seconds we haven't accumulated any change in height yet. But this function is telling us, starting from 0.6 seconds, how much the height has changed, right? How much the height has changed. All right, so what does this point right here mean? So this is the point, it looks like, what, 1, comma? So that point means what? Well, this tells the story right here. So in the context, what does that point 1, comma, negative 0.75 mean? Let's get out the wheel. Spin the wheel. Here we go. You ready? Give it a spin. Where's Michelle Galvez? Michelle. What does that point mean?
It means that at 1 second, the constant rate of change is -0.
Well said. That point represents that at 1 second gone by, the rate of change of the height of the flag is negative 0.75, right? The point represents two quantities taken together, right? It's a correspondence of a time in seconds along with the corresponding rate of change. Okay? So how about this one? So this looks like, is that 2.3? What's that point? That's 2.3, negative 0.75. Same thing. That point says that at 2.3 seconds, the rate of change is negative 0.75. So when you look at this red line, what does it consist of? What is it? That red line. What is that red line all about then? Is it a stick? That red line is the rate of change. Agree with that? No, it's not the rate of change. That red line is not. Just like this point is not a rate of change, right? This point isn't a rate of change. What? It's a correspondence of two quantities taken together. So if we think of the whole red line, the red line is representing what? What are you looking at when you look at that red line? Okay? But what does it... So I could be asking this question about any graph. When you look at a graph... Yes, sir? No, it could be this. It could be any graph, right? So I just drew a generic graph. You don't know what quantities it is. I'm asking you, when you look at that curve, what is it? And that's not slope. Yeah. Okay. Yep. It's a relationship. But that curve itself is what? Thank you. Yeah, go ahead. Points. It's points. When you look at a curve or a line, a graph, it's points. It's a bunch of points. It just takes too long to draw it that way, right? Ugh. That's why we just go, because it's fast. But that doesn't mean you forget what it means. It means a bunch of points representing, some people said a relationship. That's right. Those bunch of points represent at every moment in time, the correspondence of time and rate of change. But when you see graphs, lines, curves, your first thought is, oh, that's a bunch of points, and each one of those points is showing me a correspondence of the two quantities. Okay? Graphs are a collection of points. Okay, so now this graph, I just want to do a mini crash course in GC. Now, most of you have, there was only one person having difficulty, so I guess all of you got it downloaded successfully. So just do a little crash course here. So when you open up, so you don't have to do this if you can just watch and then check the video later. But when you open up GC, you're going to get this is called a file window like this. And this purple box is representing a command line. So the first thing you need to know is that you can just use it as a calculator. You can just put in numerical calculations, and it will always give you whatever that equals then is whatever the current total is. So I can go ahead and edit it. I can say divide that whole thing by pi. If you type pi, it makes pi, and now it gives me the new value of whatever that expression is. Okay, so you can copy and paste. I can take that and copy it. To start a new command line, you're going to do command return, or on PC, control return. It gives you a new command line. And so now I can paste that, and I can take the square root of it. Gives me that. So you have a nice visual of it, and it always gives you the current value of whatever your expression is over there with the equal. So it makes for just a nice computing calculator. Okay? So what about this function? So we had this function a sub h. So a sub h, what was the net accumulation of height? So if you do control, this isn't crucial, but if you do control L, you can get a subscript, but don't worry about that. But so if you want to make a function, here's the key. You don't want to do normal parentheses. That's not gonna think it's a function, it's gonna think it's multiplication. So when you're setting up a function, instead of shift 9 to do regular parentheses, you want control 9. So if you do control 9, those parentheses mean you're talking about function notation, right? Function notation. So we said a of x equals, and what was it? Negative 0.75 times x minus, now that's shift because we truly want multiplication there, x minus 0.6. Okay, is that the function that we defined? Do I have it right? Okay, so there's the function. So now, if I start a new command line, so that simply defines the function. It says, okay, here's this relationship between my independent variable x and my dependent variable, which we're calling a sub h of x. Okay, and this is the function called a sub h. So a sub h is the name. This whole thing over here on the left is function notation. And then the right is the rule telling us how to get values of the dependent variable given a value of the independent variable. Okay, if we want to graph that function, like the picture that I showed you, that's where, so lowercase y and x in GC are reserved for telling the software to graph. So I want to graph on the y, on the vertical axis. What do I want to do? I want to graph values of the dependent variable. So what will I write in? If I want on the y-axis, I want to put values of the dependent variable. So I'm going to type. So, yeah, someone said it, a sub h of x. So that right there, function notation gives me values of the dependent variable. Okay, so copy, and I can just copy and paste it in there. And so now you see that I have the ability to graph. Okay, and so then I get this graph. But what did we say? This function is really about what? Starting at 0.6. So I can restrict the domain in that graphing line where I graphed it, I can say comma, and I can say only show me x values greater than 0.6. And now it looks like the graph that I gave you. If you want to zoom in or out, you can do that here. So I'll zoom in once. And now we've got the net accumulation of the height of the flag starting from 0.6 seconds since the flag was lowered. All right, so that first point that I asked you to define, or asked you to, no, not there, where is it? Here. Was that at point, looks like it was at 0.8. So I want to graph that point. So to graph a point, you're going to hit Control 2. Hit Control 2. This will plot a point, and so I want to plot that point. So what is the x-coordinate of that point? If you're paying attention, 0.8. And what's the y-coordinate of that point? Oh, okay, so yeah, look. Right now in our file, this function has been defined. So a sub h of x is any value of the independent or the dependent variable that you want. So what do we want? Yeah, so rather than make a new command line and figure out what a sub h of 0.8 is, we can just put that here. I did that. Okay. All right, so that's going to plot a point with x-coordinate 0.8 and y-coordinate a sub h of 0.8. This represents that value of the function, that net accumulation, when the x value is 0.8. So when I graph now, it shows us the point. I can also just, if I want to know that value, I can just put that on a command line. So if I do a command line of 0.8, since this is a value, it's going to tell me what the value is. This is going to be super important all semester, so please retain this. Remember this. Once you define a function in a file, now you can use function notation, and it will do the work for you. It'll tell you, okay, here's the value of that function when the independent variable is 0.8. So negative 0.15. So to everyone, find a partner, someone next to you, and in the context of the flag, explain to each other what that ordered pair means. What does that ordered pair mean? 0.8, negative 0.15. Go. So everyone's talking to somebody. Okay, let's spin the wheel. Where's Sabrina? Mango. Sabrina, tell me about this. What does this mean? 0.8 comma negative 0.15.
At 0.8 seconds, the flag's height is decreased 0.15 meters since 0.6.
She said at 0.8 seconds, the flag's height has decreased 0.15 meters since 0.6 seconds. What do you think? Is that what you said? She nailed it. That was awesome. Yeah, exactly. Exactly what that point means. Okay? All right. Any other questions on the homework? Questions on the homework? Getting ready to move on here. So that's the easy stuff. We're getting a little harder today. So we're on this journey, right? We're on this journey of kind of built a crash course in what's the calculus behind. You know how fast the quantity is changing at every moment, and you want to know how much of it you have at every moment. Okay? Principle 1 was rate of change. Principle 2 was a net accumulation function. Principle 3 is changing rate of change. So far, everything we've talked about has been about constant rate of change. Okay, but in the real world, there's most things, many things, have a changing quantities, have a changing rate of change. Okay, so now we're going to adjust our rate profile of the soldier lowering the flag to this. So, 30 seconds. Talk to the person next to you. Why does this rate profile make sense for lowering a flag? Why does this rate of change profile maybe make more sense if a person's lowering a flag? Go. Okay, so I saw lots of you doing this, right? And that's it, right? Because so when the soldier gives a pull, that's when the negative 0.75 seconds is. But then what happens? There's a pause, right? So the rate is going to, for a moment, the rate is going to kind of slow way down, maybe even stop for pause for a moment, and then the next hand comes and does it again, right? So looks like about every half a second, the soldier is giving the rope a yank, right? And then so in between those yanks, the flag pauses. So given that new rate profile, can you sketch the net accumulation function starting from 0.6 seconds? Just a rough sketch. A rough sketch. Everyone give it a try. So now, if this were the new rate profile, what would the net accumulation function look like? What would the net accumulation function? Take about a minute, see if you can come up with it. Okay, so just take 30 seconds to compare with the person next to you, see if you have something similar.
Yeah.
And then compare it to this. Did you get something like that?
It's the same.
How many people got the general idea? How many people got it? The general idea of that. Okay, and if you didn't, does it make sense? Right? It's still going to be this downward trend, right? Like what we had before, but at these in between the hands, right? It's the change in height is going to there's not going to be a change in height when there's that pause. So that's why you have a little time going by with no change in height. That's those flat parts. Okay, so we talked about, so this rate of change, this is how fast the quantity is changing every moment. That's the given. That's the thing we know. We want to know how much of it we have at every moment. Okay? And so we call this the rate of change, we're going to call R sub h. Right? This is an exact rate of change function, the thing that we have, we're given. Okay? How much of it you have at every moment, in this case that would be height. Well, that's net accumulation of height is it's like almost height, right? It's so close. How would we get height from net accumulation of height? We just want to start with what? No, so if we want height, not net accumulation, then we just need a starting height, right? And if we had a starting height and we combined it with net accumulation of height, then we'd have the height profile, right? So that's how much we have at every moment, right? So we're given our rate of change function, and we want to come up with an accumulation function, okay? Net accumulation function is almost the total accumulation, right? So it's just one step away, right? So it's virtually the same. All right, so this is the big question. And so that's our a sub h of x, right? That's what we called a sub h. So given the exact rate of change, what's the exact accumulation? And so now that we have a changing rate, we have this question. How do we write the net accumulation function when the rate of change is changing? All right, when we had constant rate of change, it was easy, right? It was really easy because we knew what? dy equals m dx, and we just kind of wrote down the function. But if the rate is continually changing, this is a different animal. This is harder, right? This is harder, and so we need to devise a scheme to figure out net accumulation when the rate is continually changing. Okay? And so here's how we're going to do that. Some of you might remember. So the first thing I'm going to do is I'm going to break up into periods of, and I'm going to choose 0.35 seconds. We're going to call those periods delta x. Delta x are fixed change in x that we're going to break up this thing, and so we can start passing out now. We're gonna break up the function into intervals of 0.35 starting at 0.6. And then we're going to build a net accumulation function based on, here's the key, constant rates in each of those intervals, right? Because we know we can do it for constant rates, so we want to take advantage of that. Okay? So we're going to break it up into intervals, and then we're going to force a constant rate in each interval, and then we know we can do the math to get net accumulation. All right, so that function is going to be what we call, we're going to make constant rates here. We're going to call that function R. So what about in that first interval? We want to get a constant rate that estimates the real rate in that first interval. What would you say? So looking right here. So in this first interval, what constant rate would estimate the true rate? Yeah, it's negative 0.75 the whole way, right? So that's easy. So we'll just throw a constant rate bar on there, and that's going to be our negative 0.75. Now what about in the next interval? We got this greatly fluctuating rate, but we need one rate that's trying to emulate that or simulate it. What one rate would you say? Something around what? Negative 0.75 again? Would that be a good kind of overall estimate of what the rate is in that interval? 0? No, so it starts at the bottom, goes up to 0, and then pretty much goes back to the bottom again. So if we wanted to pick one rate kind of like the average, right? Kind of like the average of all the rates. So I picked negative 0.4. So I picked a constant rate of negative 0.4 there. What about the next interval? So it doesn't have to be perfect. So we're just getting something on the page. It's mostly the negative 0.75 again. So I'm just gonna do the negative 0.75. Okay, now what about the next? So the next interval has all the rates from negative 0.75 to 0, but then it has this little part here there where it's all negative 0.75. So if I was comparing it to the negative 0.4, would it be more negative or less negative? More negative, because it's got this little part that's like all negative there. So I called this one negative 0.5. A little bit more negative, because it has a little bit more in the interval of a lower rate of change. And this next one, kind of the same thing, it has even more. So it kind of, you see like everything from 0 to 0.75, but even a bigger stretch of negative 0.75. So more or less negative than 0.5, negative 0.5. Again, more negative, so this time I called it negative 0.6. Okay, so do you see what we're doing? We're reproducing this rate function the best that we can with constant rates. So I'm like trying to simulate, I'm making a new function that's trying to simulate the one that we're given with constant rates. Because we know the math of constant rate of change we can accumulate, right? We can calculate amounts of accumulation. All right, so this next one looked like kind of the mirror image of the one we just did. So I did negative 0.6 again. And then the next one was the mirror image of the negative 0.5. So I did negative 0.5. And then the last one I did was negative 0.75. So this is principle number 4. And this is pretend rate function. Pretend rate function. It's pretending to be the real rate function. It's kind of like the best we can do with constant rates in these big intervals. Anybody have does the idea make sense? We need to get to accumulation, and we've got constant rate of change allows us to do that easily. So we take a changing rate function and we change it into a bunch of constant rates so we can do the math. So you have this table, and everyone have a sheet. Everyone have a sheet I gave you? So you have this table. It's got 4 columns. It has time elapsed, and that's basically the start of every interval. And then approximate rate of change, the R function, approximate change in height, and net accumulation of height. And so that net accumulation of height is something of our net accumulation function. It's just going to be like a set of points, but it's kind of like building that net accumulation function at a series of points. So you have some questions to answer there. The first question is, why are the columns staggered, offset in the way that they are? So you want to think about that. Okay, so that's done for a reason. And once you understand that, it should make perfect sense why those columns are staggered the way they are. Okay, and next is what key concept allows for computing the approximate rate of change of height in each interval? That's your third column there. And then from there, you want to fill in the 3 empty columns in the table. So I'm going to take So column 2, we already did it. Why does it make sense that it's staggered with column 1? Why does it make sense that column 2 is staggered with column 1? Yeah, so it's a rate of change for a whole bunch of x values, right? Starting at the one kind of above and ending at the one kind of below, right? So it's about, that second column is about that interval between successive x values where the rate stays the same for all those x values in between. Does it make sense? That should make sense. Do I have the second column right? How do we get approximate changes in height now? Here's the key, right? This is the whole reason we did this. This is equal to what? dy, right? These are little dy's for each interval, and we can calculate them by m dx. What's m? Whatever it is in the interval. Right now it changes, right? In each interval, we got a different constant rate. So we're going to use whatever m is for that interval. And what's dx? So dx now is our delta x, which stays the same. That's our, what, 0.35? So you're going to take your rate times 0.35, and that's going to give you these little changes in height, right? These little changes in height for each one of those intervals of 0.35 seconds. So now how do we get so approximate net accumulation of height? So this is now accumulating height, right? So what, say I want to get that value right there. I remember maxim. Where's maxim? How do I, so just give me just a general idea of how do I get that third net approximation accumulation of height in that one right there. How did you get that?
You add like the 3 approximate changes in height before that.
Okay. Yeah, so it's going to accumulate, right? We're going to have a little bit of, we're going to have the change in height from the first 0.35, and then the change in height from the second 0.35, we're going to have to add that on, right? To get now the total, or the accumulation of change in height. So each time we're adding what we had before plus the new change in height from the new interval. Is that what you did? So that should make sense. And when you do that, here's the values I got. And somehow they got moved. Hold on a second here. That's better. Okay. There we go. So see if you agree with these values, especially. So if you got the last column, then you're in good shape. If you got the last column, then you can assume that along the way was correct. So the first column and the last column together then make somewhat of a skeleton of our new a sub h function. Because we have a bunch of what? Bunch of values of the independent variable, or time since the flag started being lowered, and corresponding accumulation of height since 0.6 seconds. So the first and fourth columns then are forming kind of a skeleton of this function that we're after. So it's kind of like we're making progress. Are these values the true values of accumulation of height of the flag? No, because they were based on this rate function that was kind of awful, right? I mean, we're doing our best, but it's not the true rate function, and that's what we're after in the end. We want the actual net accumulation function for the actual blue rate function. So let's talk about the next step in that. So let's just talk about principle 5. So to do that, I will go to, see here. All right, so I'm showing 0.35. Okay. So the first thing with this is, so here's our original rate function. We got our intervals of 0.35. And what we did was we kind of tried to eyeball it. We said, what's the best constant rate for each interval? Like, that's approximating it the best. But that's not really very systematic. If we all did that separately, we'd all get something different. So there's a kind of a more systematic way to make that pretend rate function. And that is, rather than eyeballing it, we want to just go ahead and take the actual rate at the left side of each interval and let that be the constant rate for the interval. So what does that look like? That looks like this. So rather than eyeballing it, just take the rate at the left side and then let that be the constant rate for the coming interval. If we did it that way, then we'd all get the same thing for the pretend rate function, right? We'd all get the exact same pretend rate function. We'd pick off the real rate on the left side, and then that would be the pretend rate for that whole interval. We'd all get the same thing because we'd be using the same method and this exact rate function. Okay, so when we do that, here's the approximate rate function approximate net accumulation function that we get. And we know what it's supposed to look like, right? So how are we doing with this? Good or bad? So the light gray line, the light gray curve is the actual net accumulation function that we're trying to get to. And the pink one is based on this blue pretend rate function. So good or bad? It's okay. It's kind of following the general trend, but it's certainly not exact by any means. Like right now, it's not. It's kind of quite significantly off. Now it's really off, trying to come back and find its way. Okay, so but we want exact, right? So in the scheme of things, this is not good. This is not good. So what's the key to making a better approximation function? How can I get a better approximation function? All right, last of you, yeah. If you make smaller intervals, so up here I can change delta x. Here's delta x of 0.23. Let's make it even smaller. Here's delta x intervals of 0.1. And that's principle number 5. Smaller intervals means a better pretend rate function and a better net accumulation function. Smaller intervals gives us a better pretend rate function and a better net accumulation function. Okay, so this afternoon I'll start compiling your homework for next Wednesday.